Welcome to Physics 210, Day 7. So for today's example problem, we were really just playing with gravity and the whole idea of gravity not always being equal to 9.81. So all we have is we have a bunch of different positions, and we're determining the gravitational constant at that position and your weight. So the simplest place is we're going to talk first about the North and South Pole. So I'm going to just do these one at a time for space reasons. So we're told that if you are standing at the North or South Pole, you are a distance of we're going to 6,356.752 kilometers, which means that I can go ahead and change this immediately to meters, because we're going to be working in meters, away from the center of the Earth. We know, and I'm going to put this on this side, we know mass of the Earth. The mass of the Earth is 5.9722 times 10 to the 24th, and I did run out of space there, kilograms. And we do know this is just, that's not a, we do know the gravitational constant for all of our equations is going to be 6.673 times 10 to the negative 11th Newton meter squared per kilogram squared. So that is the big G to use instead of little g when you're using this version of gravity. So with this, we have and then we are told that mass of U is 70 kilograms. Is it U? Yep. So that is what we have. And the first thing we can do here is we can say we want the acceleration of gravity at that point. So acceleration of gravity is independent of the thing it's acting at. So acceleration of gravity is just going to be capital G times the mass of the thing providing the gravity, so in this case the mass of Earth, divided by the distance you are away from it squared, so radius squared. I do want to be careful with the fact that I am calling this R. This is a distance from the center. So it's the radius of the Earth, but it's the distance you are from the center of that piece. Please don't go trying to have things because of that. So all we have to do to figure out the acceleration of gravity here is take our 6.673 times 10 to the minus 11th Newton meter squared per kilogram squared. Multiply that by, right in my face line, perfect spot, Roy. Mass of the Earth, 5.9722 times 10 to the 24th kilograms. There is a line there. You'll have to trust me. Divided by our radius squared, which our radius is right here, 6,356,000 752 meters. That whole thing is squared. Woo! And that gives our acceleration of gravity, which comes out to 9.862 meters per second squared. I'm going to erase this just because it's right where my head is. And we can say that north-south pole acceleration is 9.862 meters per second squared. Okay, and from that, how do we get the weight? Well, all weight is the force caused by gravity on you. Force caused by gravity is mass times gravity. So this gravitational constant is that number right there. So instead of using 9.81, we're going to use 9.862. And we have that our mass of 70 kilograms times 9.862 meters per second squared. We're going to get our weight is a force. It's going to be in newtons. So we have a weight of 690.3 newtons. Note that I could have done this in the opposite, done this by just writing my other equation. My force is equal to gravitational constant times mass 1, mass 2. So this would be the mass of the Earth. This would be the mass of you divided by r squared. That's going to give me exactly the same number because all I've done is I've multiplied this equation by this second mass. And that's all I did here. I took the number that came out of this equation and multiplied it by this second mass. So that is North and South Pole. Well, at this point, you're probably quitting the video because we're going to do the same thing over and over again. But in case you don't, I can say that the next one that we're after is the equator. The equator, we're told, has a radius distance of, 6,378,132 meters. Everything else that's going in here is the same. I'm going to put it on this side. Now, acceleration due to gravity is going to be capital G times m over r squared. This is mass Earth in this case. We can say that this is going to be equal to 6.673 times 10 to the minus 11th Newton meter squared per kilogram squared times the mass of the Earth is going to be 5.9722 times 10 to the 24th kilograms divided by my radius squared. My radius was 6,378,132 meters. And I have to square that entire thing. That number comes out to an acceleration of 9.796 meters per second squared. What you're hopefully already seeing here is that our 9.81 not too terribly off of either of these pieces. reasonable approximation. All we have to do is take this number, and if we multiply it by our mass, so multiply it by 70 kilograms, that is equal to our weight. That's mg is all we've done there. When we do that, wrist starting to get sore, so I'm just going to go ahead and skip writing it out. That weight comes out to 684.4 newtons. Okay, now the highest point on Earth, as defined by physicists, is the furthest distance from the center of the Earth, which is not Mount Everest, which is 6,882.3 kilometers. It is Mount Chimborazo. I hope I'm saying that right. Mount probably not. Oh, not spelling it right either. Chimborazo, which has a distance from the center of the Earth of 6,384,400 meters. Okay. We're going to go ahead and plug that in. We've got my acceleration due to gravity is going to be equal to capital G times mass of the Earth divided by my radius squared. Trying to save the marker here a little bit as well, but that comes out to 6.673 times 10 minus 11th. There's a dot there. Sorry, marker is dying on me. Times the weight of the Earth, 5.9722 times 10 to the 24th kilograms, divided by this 6,384,400 meters, that whole thing squared, which comes out to an acceleration of, let's see if I can, acceleration of 9.777 meters per second squared, and a weight, when you multiply that by 70, apologies. This guy is going to be 684.4 newtons. The other one, I didn't actually ask you for, 6.796 times 70. That is, 9.796 times 70, 685.72 newtons. Okay, now the pen decides to start up, which means that from our minimum distance, can't really see that with that square there, from our minimum distance with our north and south pole to our maximum distance from the center of the Earth with Mount Chimborazo, we have a difference of 690.3 minus 684.4 newtons. So our mass has changed by 5.9 newtons, which for perspective is easier to work in metric, but you guys are going to relate more to this is 1.33 pounds force. That is not terribly different, even though it's a difference of, let's see, 28,000 meters in height. I mean, this is more than the difference between the height of Mount Everest. Your weight is changing by 1.33 pounds force. That is not a whole lot. So something to keep in mind here. But that's the problem. Take care.